Okay, let's look at example 4 from your notes that we didn't finish yesterday. We're going to switch this problem a little bit. We're going to do a D. Weiland problem. We're going to look at the volume of the area bounded between these curves, 9 equals, or y equals 9 minus x squared, x equals 0, y equals 0, rotated around the y-axis. So we can kind of get rid of this stuff. I think a lot of people, they have their struggle when they try to look at the space that they're dealing with. We have to consider, what does that original area look like that we're rotating? And this isn't too complex of a function, but if you consider the worksheet that I gave you guys, there are a couple examples on there where you're like, okay, what is the region I'm looking at? So if I draw my x and y axis, what does 9 minus x squared look like? And it says that I'm bounded by x equals 0 and y equals 0. X equals 0 is the y-axis, and x equals 0 is the x-axis. And so this is the region that we're looking at. That's my area. Yeah, yep. So because I'm rotating around the y-axis, it'll end up covering that same area generated. So this is what we have. Obviously, crosses up here at 9. Anybody know where it crosses down here? 3. And as we draw then this portion, we see the rotation. So yesterday I drew those kind of arrows circling around. You guys said you like that. And if you take any rectangle, and you just simply spin it around and rotate, you can see how you get, one of those discs. The more you kind of practice drawing this stuff, the better you get at it. So I got 3 discs on there right now. I'm going to draw one more just because I'm having a good time. So okay, so you can see how I'm stacking these discs on top of each other, right? So let's pull out just one of these discs. To take this disc right here, I'm going to pull it on out of there and look at what I have. Got this, it's a disc. But we start with this. What is the thickness of that disc? It's dy. It has vertical thickness. Therefore, my radius must be in terms of y and not in terms of x. But as you notice right now, we say that the distance looks like it rests against the function, which is 9 minus x squared. So I have to solve for it in terms of y. So if I add the x squared, I get x squared plus y is equal to 9, or x squared is equal to 9 minus y, and square root both sides. X squared is the root, x is the root of 9 minus y. So therefore, this is my radius. Now, I'll be honest, you guys, over the course of doing these problems, every once in a while when I write it in terms of y, I start to question myself if it properly represents the radius. So let's look at this bottom washer sitting all the way at the bottom. What is the radius there? It's 3. And so the y, what is the y value at the bottom right here? 0. So if you plug in 0, 9 minus 0 is 9, and the square root is 3. So did that give me the appropriate radius? Yeah, and then as I go up here, what's the radius all the way at the top? What's the y value? 9. So if I plug in 9, 9 minus 9 is 0, square root is 0. So it looks like this does appropriately represent the radius. Because we can tell by the drawing that the radius should always be between 0 and 3. And in fact, we came up with those values. So sometimes I like to do that to check my work. Well, let's find an expression for the volume of this disk. The volume of the disk would be the area times the width. And the area is pi r squared, and the width is dy. So I have pi times the square root of 9 minus y squared dy. That's the volume of one of those disks. How many disks do I want to find the volume of? An infinite number. And we say that like it's no big deal. We just throw an integral sign in front of you. I have pi. What do we get if we square that? 9 minus y dy. And now I have to look at my bounds. Should my bounds be x values or y values? Y values, because we're in terms of dy. Here, I start stacking at 0 and I go all the way up to 9. So what mistake do you think people would make? 0 to 3. But you have to consider how you're stacking these disks. 0 to 9. Now, I know this isn't easy. I know it's extremely conceptual and involves a lot of geometry and spatial reasoning, but you guys are doing good. So I get pi times, what's the antiderivative of 9? 9y minus y squared over 2. Evaluated at 9 and at 0. So we get pi times 81 minus 81 over 2. Well, 81 minus half of 81 is just half of 81, right? I guess if you want to find common denominators, 162 over 2 minus 81 over 2 is still 81 over 2. It works out a lot of times in these type of problems where you're taking a number minus its half or a number minus its third, or just kind of works out. Just the way it works out with the calculus. Okay, and so our exact volume is 81 pi over 2. Please look at your worksheet. Matt, you need one? I'll have to look. I know I've got one sitting around here somewhere. Yeah. Okay. Your worksheet. So I'm just saying it's in case Dulitzer, or who else is missing from this class? Sam Chalmers. So if you look at your worksheet, problem 1 should be very straightforward. Problem 2 should be very straightforward. Problem 3 is a dy problem. It should work out real nice. Same with problem 4. Should work out real nice. 5 is a good problem. 6 is a little bit trickier, but not too bad. Not too bad. Number 7. Number 8 is the tricky problem. Number 8, just a hint, you have to set up 2 integrals for number 8. Number 7 is a 1,296 pi over 5. I'll show you. I want to be clear that what do you get to use on this test? Everything. Okay, you get to use your notes, your worksheets, your study guides. So you really want to make sure, you guys, that your worksheets and your homework is right on, because that's the work that you get to use. Okay, so the rest of the time is yours. I'm going to answer the first question from Sarah. What? Yep.